Start recording. Okay, so we are online now. It is officially recording. I have now a little bit better. Six student out of almost like 12 or something students. 50% students are not here. I don't know because of the weather effect or whatever. I'll send an email to everyone not to miss any more classes. I'm gonna strictly enforce it probably by doing some grading on it. Uh, if not, then we'll talk in person, whatever reason. Uh, if it's excused absence. So as I was saying, the agenda today, I'd like to start. This is a pretty long class, right? We only have two classes. A very important topic: heat transfer. The first one is on Tuesday, and the other one is Thursday, and we do have a 1 hour 15 minutes. Let's start with this one. As you can see, it says no grade will be reported. So what are the things we are seeing here? Stephen Boltzmann constant didn't you didn't learn that much. Radiation equation you didn't learn that much. I barely touch on those. I know that we'll learn those things. Other than those, emissivity I did talk about it. Absorptivity I didn't talk about it. So you can kind of skip the emissivity, absorptivity, radiation equation, Stephen Boltzmann constant. Other than that, you should be able to answer the conductivity and convection coefficient and the other questions that I have: heat flux, heat transfer rate, conductivity, all those things fairly easily. Why don't you do that? No grade will be grade will be assigned for this assignment. I'm giving you like 5 minutes and try to use all 5 minutes to your fullest. Okay. Once you're done with that, I'm gonna immediately show you the solution manual. We'll talk about it as well, and you should be taking the notes by seeing the solution manual if you have anything. All right, these are very important thing. I mean, oftentimes you'll be seeing me giving the quiz. I mean, plus last 5 minutes, 10 minutes, I will invest on that. Maybe like every few classes. Very important thing for you. Okay, that we're gonna give you the encouragement to study at home. I mean, I know some students just come here, listen, and then do homework at the last moment, barely doing anything. Some students are very punctual though. They do everything on time. I know that. So this is the way of engaging everyone all the time. Okay. Try your best to answer all the questions. Okay. Start writing it in class. And to time it, I said 5 minutes, 1 minute. Okay. It's 10:09. By 14, everybody should be finished. Okay. And if you know those radiation questions, feel free to answer them as well. up? It's a non-graded quiz. I'll be getting a paper back from you. What I'll be doing, let me show you the answer, okay? And let's discuss it that. So I have the answer written in different paper, okay? So let's start with the question number one, I guess. So briefly explain the terms below. I'll just talk about them. I'm not going to write it because all those things are in your notes. You know that? Notes means like your class note and the PowerPoint that I uploaded. So the first one is conductivity. Conductivity is K. In conductivity equation, conduction equation, you have seen the K, you know the units of that, and it is the property of a material. In other words, you can get the value of the conductivity for any material from the appendix of your textbook. Everybody have the textbook? So you have to get a textbook. I did emphasis on last class. Any Samuel version or any incorporated version or any classical heat transfer book really doesn't matter. Every book does have the same thing. But for appendix purpose, I would encourage you to get a Samuel so that way you have the appendix, okay? Needed. I'll upload the appendix in Brightspace. Means I'll gonna upload the PDF of it appendix for both books. You can print it if you have a different version of that, but if you have Samuel, that you don't have to print that. Is it clear to everyone? All right, that's so important. The thing that I just mentioned. All right, so conductivity. Any question with that? The unit is watt per meter Kelvin. Remember from last class? Okay, it's a property appendix. It is part of conduction equation. It is expressed by K. So all those things, whatever I said. Okay, then emissivity. David and Steve, you guys were thinking it's in a different classroom, right? That was my yeah. Fair. I thought I sent an email last week. I forgot to send another reminder that officially it just changed. Anyway, so from now on, this is our classroom. There's a different class over there. Obviously, I've probably seen that, right? So absorptivity, emissivity, those are two radiation terms. Emissivity, I did talk about it. Remember the radiation gun that I was talking about right in the last class during COVID, everybody was using that, right? So when you are using the radiation gun, you're getting the temperature, but one thing oftentimes people ignore, put the emissivity of that particular object that you are getting the temperature. Okay? So like you're getting my temperature, you need to put my emissivity of that forehead. Make sense? And the forehead emissivity, this top surface emissivity, that surface emissivity is not same. Emissivity again is a property of the material. Make sense? But we are getting somewhere close the result when we're getting the temperature from radiation gun. We're getting somewhere close because the emissivities of those things are very close. Okay, not always. Like brighter surfaces really lower emissivity, darker surfaces really higher emissivity. Like if you have a perfect black body, then you could assume the emissivity is 1 or 100%. Is it clear? Those are the things you learn slowly, okay? But this is just the overview. Moving to the absorptivity. So absorptivity is again a radiation property. That might be something you learn in physics class, right? Yeah, I don't know if you remember absorptivity, reflectivity, transmissivity. If you learn those three things, if you add those three things, then it become one. In other words, let's try to understand. I mean, see what I'm doing, not the answer of the quiz. Now I'm starting to give you the radiation background, which would be our topic today. Okay, and our topic, another agenda would be doing a math problem. Okay, so now moving to the absorptivity. Again, I was talking about absorptivity, transmissivity, and what is the other one? Reflectivity, right? Absorptivity, transmissivity, and reflectivity. Those three things accumulate the total radiation. So how can I understand that? Say like sunlight gives you the radiation, right? So when sunlight comes to something, everybody's listening, right? It's good. So when light, okay. So I mean, if you have something to distract you, just try to close that and focus on that. You are registered for this heat transfer class. Okay, this is all right. All right. So I was just talking about the radiation, right? When the radiation rays are like coming from sunlight on any surface, three things can happen. One is that radiation ray that is coming, all of it could be absorbed. Okay? All of it could be reflected back. Or all of it could be transmitted. Means nothing absorbed, nothing reflected, all just pass through, right? And also those three things can be combined together. Means some of it can absorb, some of it gonna transmit, some of it gonna reflect back. Does it make sense? So any combination possible. So those are the three things can happen when radiation comes from any surface. Okay, now how emissivity come in play? which what is emissivity? I did talk about it, right? Emissivity is something that has something to do with the reflection, right? Means when I'm getting the temperature of my forehead, whatever radiation is coming from my forehead is sensing by the radiation band. It's clear, right? So something is coming from here, right? Some heated ray, infrared ray, right? That is captured. You understand that, right? So does it mean like this is the reflective ray that I'm talking, or it has something else as well? So here's the point. I'm trying to give you the difference between, don't know, I'm going to write it somewhere. So here's the point. I'm trying to give you the difference between emissivity and the reflectivity. Okay. So emissivity is not reflective. Okay. But it could be same in special situation, but most of the time it is not. So reflectivity is when radiation comes here from sunlight, or say like there's no sun today here. Say like there is a very high temperature hot plate over there, or oven is running, or a stove is running. It's high temperature, right? So radiation ray is gonna come to all the surface surrounding here, right? Including me, my forehead, right? So it is gonna come here. Some is gonna get absorbed. Some are gonna feel warm, right? Some is gonna get reflected. Means if you're gonna put your hand here, if I'm very close to the stove, you're gonna probably feel some of the reflection there. Maybe minimal, but it's there. And some there won't be any transmission happen, right? So there is zero transmission. Does it make sense? So absorption and reflection, that all can happen. But emission is not only that radiation that is coming to me, also I have my own heat, right? Because I'm a heating gene, everybody's a heating gene. We have a temperature of 98 degrees Fahrenheit compared to the air, right? So we do emit all the time. Is it clear? So along with the reflection and the radiation, along with the reflection and the thing that I already have, we're gonna come as an emission. Does it make sense? All right. So that's the overall absorptivity and emissivity concept. Heat transfer coefficient. Anybody remember what is heat transfer coefficient? Where it goes, like the conductivity equation or convection equation? Convection equation. Oh, we use the term H for that, right? And the unit is watt per meter square Kelvin. Okay, remember those? All right. Remember, half of the semester will be dealing with the conduction, half of the semester will be dealing with the convection. When you'll be dealing with the convection, remember in last class that what we understood, we'll be exploring the value of H all through the semester. So we'll be given with so many different equations like Nusselt number, Prandtl number, and Reynolds number equation. Those three things we learned in last class, right? We'll be given with those equation combination for different situations, and we'll be able to find the value of H. Clear about the H? Okay, moving on. So you have the heat flux. Okay, from this point on, I'll just a little bit going with the faster pace because I have some agenda here. I'd like to finish them. So heat flux, right? Okay, so heat flux, heat flux Q double prime. You guys remember it is per unit area, right? So watt per meter square. You remember that from last class? All right. So then heat transfer rate, which is Q, that's the symbol we use, and the unit is watt. Okay, we learned this in last class, right? Then conductivity K, I was talking about it. I don't want to repeat that. So like K watt per meter Kelvin, that's the unit. Then heat transfer coefficient is H, right? That's the thing. Unit is watt per meter square Kelvin. I was talking about it. Stephen Boltzmann constant. I did briefly explain that watt per meter square Kelvin to the power 4. That symbol we used it in radiation equation. We'll learn more today, just shortly. And the value of that sigma is the Stephen Boltzmann constant is 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. Okay. And there is this number 2 question, right? Number 2 question was the equations. These equations we did learn, right? First two for sure. The third one didn't quite. Okay, the first two, as we focus, let's focus on that. Conduction equation is minus Ka del T over L. It can be also written dt. I don't know, only black color I'm gonna use. Dt over dx. Remember those, that equation? Please review that. Don't want to go through again the same thing. We're gonna very well take 10 minutes last class agenda. Don't want to do that. But please review the last class, right? We did learn. Anybody remember why we had a negative sign? Some of you did. Temperature change. Yeah, that's the thing. So heat always transfer from high to low, right? High to low. Now, when you have a del T or dt here, which is always T2 minus T1 or low to high. So to nullify that del T effect, we got to have a negative here. Okay, clear? All right. So the convection equation is very straightforward. HA del T. Del T, we did talk about it. Please take a look on the class notes. Okay. And I was talking about the radiation equation. Okay. I'd like to now go to the class note. Okay. So I can start writing the radiation equation, give a little bit more about that. And as I said, I do have just two agenda today: radiation equations, and then we'll be done with the PowerPoint, right? The thing that we started in last class, and the math problem, the first conduction math problem we're going to do today. Okay, and then you would be ready to start doing the homework. The homework is already in bright space. Okay, good. Should I move on? Any question with the quiz? Yes. You good, Chelsea? All right. I didn't ask your name. What's your name? What's your name? D4? Oh, D4. D4. My name is Roman. You can call me Dr. Roman, okay? I know pretty much everyone. So, welcome, D4. Are you a transfer student? Okay. Okay, welcome, D4. So, we're gonna, you missed two few classes, right? There are notes and everything. After the class, talk with me. I'll try my best to, put you up to speed. All right. Um, so, here, okay, this is the slide. This is where I stopped kind of in last place. Okay, let's just talk about it. So first of all, let's try to understand what you're seeing here. Okay, so we have a plate. This is the shaded area, and here underneath the plate, some of the things written. What is that? Surface emissivity epsilon. You guys are familiar with this? Okay, by the way, you're not gonna have the access like Madeline and Defoe. Defoe is fairly new, but Madeline, you're not gonna have the access of one node, right? Like last time, because for federal regulation, we are not allowed to share this one node. But this node is in bright space for your reference. You can download it. You can do it later. But anything that I'm writing it here, you got to diligently write what I'm writing, because this class note, we are not allowed to share it anymore digitally. Okay, but you can write it during the class time. Okay, I put this class in record, so the video is already in record. Once the class is done, I'm gonna put a YouTube link in bright space, so you can watch the whole thing what happened in class. Okay, but you should be taking the class note, whatever I'm writing. Everybody should be serious. So okay, come back here. Surface emissivity, did this epsilon, I did talk about it already. This epsilon is a Greek letter, and emissivity refers to how much of the radiation coming from any surface, right? Any surface can radiate, and we'll explain a little bit more on that. Let's just highlight that E term first. This E is referring to emission, and epsilon is referring to emissivity. Okay, what is the equation for E? It's written here. I don't want to rewrite that. Okay, I'm highlighting that. So again, this E has this epsilon and this EB. Now, what is this EB? This EB is called emissive power of the black body. Okay. Now, let me give you the EB equation here. EB is sigma Ts to the power 4. Okay. Now, there's this sigma. I did talk about it. It's a constant, right? Stephen Boltzmann, these two scientists, they invented that. I showing you the value is written here on the slide as well, right? 5.67 10 to the power minus 8 watt per meter square Kelvin to the power 4, right? So that's the sigma. That's a constant. We don't worry about it. We just plug that, right? So there is this temperature Ts. What temperature you think is referring? That's the surface temperature, right? The surface temperature. So that's Ts. So that's the EB for black hole. Now this term is referring to that this EB refers to the emission that from happened from a perfect black body. Okay, so why it is a perfect black body emission EB? Because that could be the highest emission happen. Okay, now in a summer, in a very sunny day, when you go out with a black dress, you feel warm or you feel more hot, right, than the light dress. You know, because black body has the capability of absorbing the highest amount as well as has the capacity of emit the highest amount as well. This makes sense? So if I have a black dress or darker dress during summer in a hot sunny day, you're gonna feel very warm. Same time, it will gonna radiate or emit its maximum. This makes sense? Okay, and it can happen, the maximum amount can happen if it's a perfectly black. Okay, perfectly black surface, right? So that this EB is referring to that much of emission can happen from that perfectly black surface, right? But obviously, not everything is perfectly black surface. Okay, there are lighter surface like here, or black surface like here. So what happened from the lighter surface? Obviously, you are expecting less of emission, right? So how to quantify that? How much of the percentage of the perfect black surface that lighter surface is emitting? You understand what I just said? How much of the percentage? And that percentage is referred by emissivity or epsilon. Is it clear? Everybody got it? If you're following me, what I said? Okay, perfect. So, so if you understand so far what I said, you actually understand this equation as well, which is E or emissivity equation, right? Equal epsilon EB. Now, I'm not wasting my time to write those same things, but you can do it. This class note PowerPoint slides is in bright space. You can print it. You can watch it later. Okay, but you know what is EB? It's written here, right? Let me take it out and try to point it out. So this is my EB, emissive power of black body, right? You can see that. This is my E is emissive power, and they have the units here as well. Watt per meter square. You see that? And did you see that the thing that I just said? Perfect emitter. I did mention about it, right? Black body, EB, perfect emitter. Does it start to make sense? Everybody? All right. So that's the E. Any question with the E or emissivity or EB or epsilon? Everybody's feeling confident or sigma, right? Everybody feeling confident with all those things I said? Okay, now focus on G. What is the G? You're seeing a wiggle line coming to a surface. Obviously that's the opposite of E, right? E is something going out from the surface. So G is, as it says, absorption due to radiation. Okay, they call it E radiation. Okay, radiation, E radiation means opposite of radiation. So radiation usually refers that you are emitting something, right? Some energy. E radiation usually refers you're absorbing something, right? And that's what the G is here. So what is the net radiation then? The subtraction of those two things, right? Make sense? Right? Something you are getting, something you are. So maybe the net would be positive or negative. Maybe the amount you are getting radiation is higher than the amount you are giving away, right? So in that case, it's the net radiation negative. Means you are actually net absorbing the radiation. Okay. So that's a very interesting fact. Like everything, everywhere is always emitting radiation, right? So now, how the radiation is in effect? Say like you are cooking something in oven, right? The cake initially does have very low temperature compared to the air inside the oven, right? So cake is emitting, oven is emitting, right? So there will be a fight. who's gonna win, right? To to bake the cake needs to absorb more from the oven. Does it make sense? Than the amount that cake is emitting. Everything is emitting, right? Is it clear? No matter how small the temperature is. All right. So now focus on the G term, right? A little bit more. So it's not that bad. It's kind of easy. So you have this G absorption, where this alpha term comes here. So what is this alpha? It's called absorptivity, surface absorptivity, right? So that's a new thing we learned here, absorptivity, right? So it can have a value from anywhere from 0 to 1, the same as for epsilon. Epsilon has a value from 0 to 1. These are the thing I'm highlighting, very important stuff, okay? So far you guys are good? All right. So this G is irradiation, okay, as I was saying before. I guess I kind of covered every term here, okay? So another thing very important that I said, in order for radiation to happen, the air temperature and the surface temperature needs to be different, right? So in practical situation, say like nobody here in the classroom, this tabletop, right? This shelf top and the air, you assuming all are exchanging radiation, right? Because that's what I was claiming before, right? Everybody's in meeting, somebody need to win. Now, air temperature and all those three things that I was explaining has the same temperature, right? Because the room temperature is 75 or 72, whatever it is, or everything is in thermally equilibrium. That's the term you remember from thermal class? Thermal equilibrium means all the temperatures are the same, air temperature, surface temperature, except us. No matter what, we have 98 point something, right? So we are, all humans are 18 G, okay? Nobody is here, okay? This surface and this air has same temperature. So in that case, no radiation, okay? As you can see here, the highlight that I have, Ts is not equal to T infinity. If you have only that case, then the radiation can happen. But the thing that I was explaining here, T infinity is the air temperature, Ts is the surface temperature, is same, so no radiation. So if you have a case like that, Ts and T infinity same temperature, no radiation, none of the equation you have to worry, no radiation. Does it make sense? And that is true for any heat transfer mode. It's conduction convection. Heat transfer requires change of temperature, right? Does it make sense? There's no temperature change, difference. There's no heat transfer equation. Okay? So you understand T infinity is the air temperature, Ts is the surface temperature, right? That's what I just mentioned. That was my intention here. T infinity is air temperature. Ts is surface temperature. Now in this slide, does everybody understand everything? Like all the parameters, all the equations, what I went through so far. Everybody understand everything, right? Any question? Okay, perfect. This is one of the most important slide, and another slide is even more important than that, which the equation that you'd be using for radiation. Should I move on? And by the way, as I said, you do have the access of that. Okay, what I just wrote here. Everybody have the access of that. And now I'm gonna highlight an equation which is the most important one that you would be using. Anytime you have this Q, which is heat rate, you remember that, right? Anytime you have a Q double prime, what is that? And the unit is watt per meter square, right? Okay, remember those always, right? So you're seeing heat flux and a subscript RAD. I mean, you guys remember a subscript COND means conduction, subscript CONV or vector is for convection, and subscript RAD means radiation, right? So you have a heat flux for radiation, right? Let's try to focus on this equation, okay? Let's just write it and try to understand it fully. And this equation does have, this is the heat rate for radiation, right? Before you're good so far? I know you just come in second week, but slowly you'll understand. So it has this sigma epsilon Ts to the power 4 minus T surrounding to the power 4. Now here's the thing, Ts is the surface temperature. Everybody wanna write the class notes, okay? Please write the class note. Whatever I'm writing, write it. Okay. So Ts is the surface temperature, right? So if you don't write the class note, what will happen? Pretty soon you're gonna get lost. And once you get lost, what I'm saying, then you're not gonna feel any interest. Slowly, you're gonna soon, very soon, you're gonna start missing the class, start not to submit things, and end of the semester you're not gonna learn anything. Okay, so try to be very punctual and very serious. This is a serious matter. So TSUR means surroundings. Okay, so that's called surrounding temperature. Anytime you see me writing TEMP means temperature. Okay, this is a short form of temperature. Now you might be seeing this T surrounding, and the other thing that you learned in last slide, I do want to write that. So T infinity, you may not see this thing before. T infinity is called, usually refers by ER temperature, right? So there is this surrounding temperature, there is this ER temperature, and this is the equation for radiation, heat flux. Okay. Now, if I'm gonna tell you, write the heat rate equation for radiation. So let me write it here. So radiation heat rate. Don't worry, I'm gonna explain everything that you're seeing. Can you guys write that heat rate equation if you know the heat flux equation for radiation? Let's see if you remember the flux equation, right? See if you can able to write heat rate equation. It's not given here directly. So the beauty of this thing, you see, anytime I'm not writing anything on this, the beauty of this slides is written here, right? This Q double prime red means net radiation heat flux, right? Make sense? So you are now trying to write what? Q double prime. You are trying to write Q red means radiation heat transfer, or radiation heat transfer rate, or radiation heat rate. Different way people say it in different books. Okay, is it the same equation? Except it does have A. We're gonna multiply. A is the area, right? I hope most of you get it, right? Because the heat flux has an equation of heat rate multiplied by area. Just remember that. So I was saying, you see, heat flux and heat rate are related by this surface area A, right? So let me write it. Surface area A, right? Heat flux, heat rate. Heat flux, heat rate. Okay, don't want to write what is heat flux, heat rate. The quiz happened over there. We did learn it. So it would be the same, except it does have this A term come in play. Okay, so oftentimes over the years I've seen students get confused with those, right? Q double prime radiation, they use that equation when they're asked to find the radiation heat rate. Okay, so they forgot to multiply the area A. We did learn why there is heat flux, what is the importance of heat flux, right? Per unit area is important because it just gives us the unit heat rate happen, or unit heat rate for different modes, radiation, convection, or conduction happen. Anyway, so let's now try to focus a little bit more here on this equation. First of all, any questions so far? I'll be done probably next 2-3 minutes on this one, and then I have plenty of time to do one math problem for sure. Any question? because this class is 1 hour 15 minutes. We really have plenty of times to go really in a nicer fashion instead of 15-minute class. Okay, so here's the thing. You see, uh, let me just take it out for now and just highlight that. So anybody remember this alpha G? What is that? Is it like radiation absorbed due to irradiation? You remember that, right? Substance. Okay, so this is G abs, means radiation absorbed radiation absorption on the surface, right? Amount of radiation absorption on the surface. Anybody remember this epsilon EB? Now there is on the parenthesis TS. Forget about it. Okay, for now. But anybody remember that epsilon EB? What is that? That's the amount of emission, right? Let me highlight that. So E is epsilon EB, right? Did you learn this here? What is that again? Energy outflow due to emission. Ever see that? Okay. You learned EB, which is sigma Ts to the power 4, right? As well. Remember that, right? All right. So now focus here. We're almost at the end. So this E is the emission, and this G absorption is the absorption, right? If you're gonna plug those EV value, which is E in this case, just 1 second. Okay, now let's just focus on that equation. So I have, so by the way, this is my final equation, right? Let me first put a box here. There's two equation. This is the heat, radiation heat flux. RAD dot means radiation. Anytime you see me writing RAD dot means radiation. So radiation heat flux, radiation heat rate, you understand that. So now we're trying to understand the detail, okay? So Q double prime rad is written as E minus G absorption, right? So before I go any further, just try to understand what is E again? The emission from any surface. What is G again? The irradiation or something that is coming to the surface. You are trying to find what? The net, right? Net. You are trying to find the net, means the difference. Whatever is coming, whatever is going minus whatever is coming onto it, right? So that's the net effect you are trying to find. That's called the net radiation, right? The net effect you are trying to find. So if you are trying to find the net effect, take a look here. If you can just plug this E equation and T absorption equation, and then you should be able to find this final form of the equation. Is it clear? Okay, again, what is E? Is epsilon EB. What is EB? Remember from last class? Last slide. It is sigma Ts to the power 4. What is Ts? Is the surface that we're talking, the temperature of that surface, right? So we understand everything about that? Okay, so now the same thing goes with that Z absorption as well, right? Let me write that, and I'm going to give you a little bit derivation here as well. So you have this epsilon sigma Ts to the power 4. The thing that I write instead of E, everybody understand that? Any question on that? All right. So now G absorption, I can write alpha G. Now this alpha, anybody remember what is this alpha? It's called absorptivity. You want me to write it on the side? So let me do that. Absorptivity alpha. Now this alpha, what could be the value of alpha? Anywhere from 0 to 1, right? Or 0 to 100%? 0 to 1. All right, this G can be written as, okay, this G can be written as alpha T surrounding to the power 4. Why I'm writing this way, and what is this T surrounding is? So take a look here. You have this surface, right, where you have a temperature of Ts, and you have this T surrounding is the dome. Now, what is this dome in a practical situation? This dome is the surface of the ceiling, sidewall, and everything, right? And Ts is the surface temperature. You understand? So the dome, you are assuming one single temperature for every surface. Okay, that's why you are calling it T surrounding. TSUR as in a subscript. Is it clear? So when you do the radiation problem, you should be able to find the T surrounding TSUR, and you should be finding the TS. All right. So let me write that here. Epsilon sigma Ts to the power 4 alpha sigma T surrounding to the power 4. Those are, as a side note, I'm just putting in the box. Now, is this the same equation of what we wrote like Q double prime red? Hmm? It is not. 0 to 1, sorry. It's 0 to 1. The 1 doesn't look 1 here, but it looks in my computer 1. Okay. It conveyed somehow differently. Okay. So is this the same equation that I wrote here? Is this the same equation? What about this alpha? Do I have any alpha here? Technically, it is not a same equation, but I'm claiming it's the same equation. But here's the thing: in order for these two equations are same, this alpha should be equal to epsilon. Is it clear? So the emission should be equal to the absorption. You understand that? It is a perfect black body, but we can assume this thing for any gray surface. Emissivity and absorptivity, when you can assume those are same, you can say this is gray surface. Okay, gray surface. It's darker surface. Let me put it this way. As long as you have a darker surface, you can use this equation. But we'll be using this equation darker surface, lighter surface, or any surface per se. Okay, and claiming it's an assumption. So claiming this equation is true, alpha equal to epsilon. You guys understand what is alpha and epsilon, right? Epsilon is emissivity, alpha is what? What is alpha? Absorptivity, right? Absorptivity says the amount of absorption can happen, right? And emissivity says the amount of emission can happen. Okay. All right. So everything's good. So I can say it this way. So this is my Q red double prime. So when, right? When what? Epsilon equal to alpha, right? Then I can write Q red double prime equal what I can write? Now does this start to make sense now? The Q radiation equation. Now, do you have to do any of the derivation when we're going to do the math? No. We'll just use this equation, the equation that I gave you. You need to know where this equation is coming from. It's not straightforward. Now you understand, right? Where it's coming from? It has the absorption, it has the emission, all those things, right? When we'll be using all those things, when we're going to learn the detail about the radiation, right? Most of the time you won't be doing the detail about the radiation. Most of the time, okay, in this class. But at the end of the semester, I'm going to teach you a little bit of the radiation, okay? There are other terms here like radiosity, view factor, all those interesting spec of radiation that we're going to learn very briefly, okay? Because it's a 3 credit hour course with a project, we never have enough time to deal with radiation properly. When I did undergrad, we had like 2 pictures per class. So in one semester, we used to deal with radiation and convection, and one semester we used to deal with only the conduction. Okay, so you have to understand. I got to cut some of the topic. It's not like I'm gonna move faster. From long time experience, I'm teaching it for 10 years. I know if I'm gonna move faster, I'm gonna lose some of you, or in some cases, most of you. I don't want to do that. So I'm gonna go with my pace. I know what pace I need to go, but just to give you a heads up, what is happening in the half of the semester, you'll be learning the conduction. Half of the semester, you'll be learning the convection. Okay, and briefly, you're gonna learn the radiation. First half of the semester, you learn the radiation. This is it. So you'll be using this equation in first few homeworks, right? To do the radiation. Okay, but remember, that's not all the radiation. That's why I had to spend like 30-40 minutes on the background of the radiation. Now you have some background on the radiations, right? At least some. You'll have even more background when you're going to read through the book. Remember, I said read the book, and my slides, like the PowerPoint slides that I gave you, is a perfect good example, right? Reference point, like what to read. The book could have endless amount of materials, right? So just look for those materials, or whatever the PowerPoint slide says. Look for those what I covered in class, right? In the book. Try to read more in the book. The book has more explanation on that. That's a proper way of learning heat transfer. Okay, everybody's gonna do that? I'm hoping, right? Okay, everybody is gonna do that. Hopefully. So now I have like around 20 minutes. That should be enough to do the first math problem. Easy math, very easy math. Okay. I know some of you can even do it by yourself. So let me go to the math, right? Without further ado. So this is the math that we'll be doing. Okay, so this math problem that we have here, let me read through it very quickly and give you some directions. If you are advanced enough, you may be able to finish it by yourself. Okay, let's see. Say concrete slab on a basement is 11-meter long, okay, and 8-meter wide. So the area of the concrete slab is given by 11 and 8. Okay, technically. So they gave you the thickness of the slab as well, 0.2 meter thick, right? So during the winter temperature are nominally 17 degrees Celsius and 10 degrees Celsius at the top and bottom surface of the slab, right? 17 and 10 degrees Celsius. The slab thickness is given, slab surface area is given. You understand therefore, right? Just the basement slab we're talking. It's like some amount of thickness, 0.2, right? The bottom surface temperature is given and the top surface temperature is given, 10 and 17 degrees Celsius, right? And they give you the size of the slab, right? So like one side is 10 and the other side is 17, right? Okay. So these are the info given, not meter. So they said if the concrete has a thermal conductivity value given as 1.4 watt per meter calorie, right? What is the rate of heat loss to the slab? Okay, and there is another question that requires the knowledge of the left side sketch furnace, where the natural gas cost given, right? This is like 1 cent per megajoule. You remember M is for mega. You will remember that, right? J is for joule. So that's the price given for natural gas, and you're asking, okay, how much of the money that to heat up the floor only for the basement? How much of the money that you're going to spend on fuel when the unit fuel cost is 1 cent per megajoule? Okay, so that's the same part. Let's focus on the first part. What you have learned already, right? Which is the conduction. It's a conduction, right? Because it's a slab, right? And slab is solid. You know, solid means conduction. And you have the equation for conduction. Everybody have the equation for conduction, right? So conduction equation is what? Like Q conduction equal what? Minus K A del T divided by the L or the thickness, right? Remember that? Del T divided by del X. That's the equation we learned in last class, right? Del X is the thickness. Okay. A is what here? You can find it, right? 10 multiplied 17 meters squared, right? So A is, and the thickness, what is the thickness, Madeline? 0.2 meter, right? So it's given as well, right? So what is the del T? The del T given, like 17 and 10, there's a difference, up surface and bottom surface, right? So del T is change of temperature, okay? So you can find that as well, right? So you know del T. Do you know the K? Is the K given? Yes. What is the K? Conductivity, right? 1.4. That's given as well. What are you going to find? Heat rate. Can you find that? Just go with the engineering format. If I were you, I will start writing like the givens first. Okay, givens, and what are givens? Like, start to write them and then find what we're trying to find, the heat rate, right? And also the cost for energy per day. Two things that we're finding, A and B. You can do it that way, right? Assumptions, you can do some assumptions here. I'll say like skip that assumption part for now. I'm gonna write it for you. But now move to the actual solution itself, right? What are the solutions here? We're dealing with the conduction, so just write the conduction equation, which again is Q equal minus Ka del T divided by the thickness, right? And then start to plug all the values to find the Q value. Can you do that? So I know most of you, the way I'm seeing the class dynamics, can do it. Okay, please do that. What I'll be doing here, I'll be also writing it myself. Okay, in case, don't try to copy what I'm writing. Try to match it to your answer. So if you stuck on anything, then there's a reference for you, right? What I just said. So that is the best way of learning things. That way you're gonna learn it, okay? Other than you just copying it. Okay, so that's my suggestions to everyone. So as I was saying, I'm gonna write it just for your reference, but please don't focus on what I'm writing too much. Try to do it by yourself. Just match it with mine. If you have any issues any place, I said I'm gonna start with the givens, right? Especially part A. There's two parts. Okay, what is the rate of heat loss? Everybody should be able to answer it, which is Q equal minus Ka del T over the thickness, right? Everybody can use that equation and find the value of it easily. So that's the first part. The second part is the daily cost. That's part B, and that's part A. The daily cost could be a little tricky. I'm going to help you on that. Okay, don't worry. Just go with the engineering format. So I'll be doing it this way, I guess. I'm going to name that the way I have it here written, T1 and T2. Okay, so I have this T1. The sketch I'm skipping because the sketch is drawn already here, right? So T1 is 17 degrees Celsius. T2 is 10 degrees Celsius. The length is 11 meter. The width is 8 meter. And the thickness T, here it says by T, 0.2 meter. The conductivity K, we all know what is conductivity symbol is for, right? It does even says concrete K, and you know this conductivity. They call thermal conductivity as well. Okay, there are electrical conductivity and thermal conductivity. That's why oftentimes you see thermal conductivity. Okay, so okay, for first time I'm writing it because this is the thing you just started to learn from last class. So conductivity K is given as 1.4 watt per meter Kelvin. Remember the unit, right? There is a difference between H and K unit, right? H has what unit? Watt per meter square Kelvin. K has what unit? Watt per meter Kelvin. Okay, remember the difference? Did talk about it in last class, right? So then the other things, that's for part B of the problem. These are straightforward, like the furnace thing, right? The furnace efficiency and other things are full cost. Okay, hardly take the class note. Okay, so furnace efficiency. Okay, so furnace efficiency is eta f. This class is gonna go usually a little longer because we have two classes, 1 hour 15 minutes classes. I know you might get a little bit bored, but that's why I had this quiz at the beginning. We spent like 15 minutes over there, so all you had to do like 1 hour paying attention, right, instead of 1 hour 15 minutes. So NF, so this eta f is the efficiency. You guys remember the eta is the symbol for efficiency. There's this cost for natural gas, right? CG is 0.1 cent, 0.1 cent, sorry, 1 cent or 0.01. Is it? I guess 0.02. I have it. I have the solution here 0.02. So correct it. 0.02. Okay, 0.02 per megajoule, right? Those are the givens. So you are trying to find the heat rate, that part 1. When I'm saying the heat rate, that Q, you see on the sketch, it's showing the heat is moving from top surface to bottom surface, high to low temperature, right? That's the Q. You're saying it's penetrating, right? It's penetrating. Okay, so there's the heat rate, part A, and part B. You are trying to find the daily cost of NG, means natural gas, right? So you can say CD, D subscriptive refers to daily. Okay. All right. What are the assumptions here? So the assumptions, three assumptions that I want to write. First assumptions. Anybody have any idea about the assumptions? We're not going to deal with radiation in this problem because they didn't give you the emissivity. Anytime they give you the emissivity, you're going to deal with that. So it's just the conduction. The first assumption you can do is steady state conduction. Means steady state means, you guys remember from thermoclass, with time the heat rate doesn't change, right? So like if the heat rate at this point during the class time is whatever amount of watt or kilowatt, say like tomorrow same time same heat rate, tonight same heat rate, every time same heat rate for infinite amount of time. That's called steady state, right? So that's the first assumption. And you know, those who took thermo, anytime I write SS dot dot means steady state, short form, right? What is the second assumption? Constant properties, right? So the K is a property of concrete. It can vary everywhere, right? You know, when you pour the concrete, the density could be different at different place. The K value could be different as well. But we are assuming no, it's same. K is 1.4. Understand? So there's the constant property, right? So constant property. Okay, what is the third one? The third one could be 1D conduction. You know, in a concrete slab, just think this way. Say like this is a concrete slab. At that corner, the amount of heat transfer, at that corner, the amount of heat transfer could be different, right? Because it's a 3D case in that case, right? And here it could be different. But we are assuming everywhere in the top surface, everywhere in the bottom surface has the same temperature, it keeps same everywhere. Does it make sense? No matter that corner, no matter that corner, no matter that middle, everywhere that you same. So I can write 1D heat conduction, okay? That's so important. 1D heat transfer. Everybody understand these three assumptions? Any question with those three assumptions? Okay. I know I said you guys are doing this by yourself, but maybe you are still keeping up with your speed with me, right? It's all right. So you had the sketch already. I don't want to draw the sketch anymore. So I'll start with part A, where the heat uh, rate equation. Now you remember heat rate equal minus Ka del T over del X, right? I just start with the equation, basic equation, right? What is my del X? That's my thickness in this case, right? So if it's my slab, that's my del X. Okay, if that is my L, okay, and that is my W, so the area can be written as L multiplied W, right? And if this is my T1 and the bottom surface is my T2, heat is flowing from top to bottom, right? You understand this sketch? Very important. Okay, if that's the case, I can rewrite this KLW as A, this del T as T2 minus T1 divided by this del X is my thickness, right? So I can say this del X equal T. So instead of del X, I can write it T. Is it clear to everyone? Just pay attention to the different notation that I'm using, right? In the first equation, I use this notation, that generic one, right? Every time you are doing a problem, you'd like to start with that first equation. Now, for this particular problem, because the A is L multiplied W, I'm going to write it L multiplied W. Because the del X is the thickness T, I'm going to write T. Because the del T is, in this particular problem, right, T2 minus T1, I'm going to write T2 minus T1. In different problem, you could have, instead of T2 minus T1, you could have T4 minus T3. You could have like T4 minus T1. Doesn't matter really. You know, the change of temperature symbol can change. but the generic one could be del T. Is it clear to everyone? The generic thickness should be del X. So you want to write the generic equation first, and then for particular problem, whatever symbol you use, you want to use that. Is it clear, everyone? Please follow that, what I just said. If you do that, then there would be less chance of doing the mistake on the problem. You see, the negative sign is going to go away right away because you're seeing clearly T2 is smaller, T1 is bigger, right? So you'll have a negative, 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 positive. The negative is going to go away. You have K values given. Can you finish the problem, everyone? Everyone understand up to this? Finish taking the notes. Finish the problem at least first part easily. Okay, do it then. Okay, I'm gonna do it as well here on the side, so you can copy. So I have minus 1.4 watt per meter Kelvin. Okay, I'm gonna write them in a parenthesis one after another, and I have 11 meter multiplied 8 meter, right? And I have this 10 minus 17, right? And you know, that's a very important thing. Change of temperature in degrees Celsius and change of temperature in Kelvin is same. You guys know that? Everybody remember that from thermo class? Let me tell you again in a slower fashion. So everybody type it in the brain. Change of temperature in degrees Celsius and change of temperature in Kelvin is same. As an example, here the top surface has 17 degrees Celsius, bottom surface has 10 degrees Celsius, right? So change of temperature delta is 7 degrees Celsius. I can say it is 7 Kelvin as well. Everyone know that, right? If you don't know that, know it now. Change of temperature in degrees Celsius, change of temperature in Kelvin is the same. Okay? Because Kelvin is 273 plus this degree Celsius, right? So, okay, so I wrote it, and the thickness is given as 0.2 meter. Now, this Kelvin cancel out. Okay? This meter cancel out. This meter cancel out. It goes so far? This negative and this negative 7 will gonna become positive, right? And you'll have a value of 4,312 watt. That's your Q, heat rate. You can also write this 4.312 kilowatt. Either way is fine. That's part A. Yes.
Should you convert that to joules per second?
Yeah, it's the same thing. Watt and joule per second is the same thing.
Right, but we need to know how many seconds.
Oh, that's for the second part?
Yeah,
let's focus on that. There's the first part. First part is done here. Everyone understand that first part? You're absolutely right. We're going to do something about that. For now, just focus on this. Anytime you write the Q, you always go with the watt or kilowatt or megawatt or, you know what I'm saying, gigawatt. Should I move on to the second one? Second part? Don't worry, if you didn't finish it, I'm going to give you plenty of time, right? And it's on record as well. So it will be uploaded. YouTube video is going to be uploaded immediately after the class, okay? Within a 1 hour or so. So you have the access of everything that happened here today, okay? Not the OneNote, but the video lecture, okay? All right, so daily cost. So that's part B. So daily cost. And after this problem, you guys should be able to start doing the homework. Homework is, by the way, in Brightspace. Okay, I uploaded it already in assignment, okay? So daily cost, daily fuel cost would be CD. You can write it this way. So you have this Q or the heat rate multiplied this time. Okay, del time means the time for that particular day that we are talking. Now it comes to the point that Matt was saying, like, you know, shouldn't you do it like joule per second? Yes, we gotta do it like so that second we're gonna cancel out, so we're gonna have only joule, right? So let's focus a little bit more. So you had this equation divided by efficiency, right? 0.9 was the efficiency. Everybody remember that? Let me give you the symbol first, so that way you know symbolically. And you're multiplying unit cost, right? Unit cost is like what? 2 cents per megajoule. Remember that? 2 cents per megajoule, right? That's a natural gas cost, not too much, right? Okay. So what now? Like just start to plug the values. Now, efficiency can be written as 90% means like 0.9. Everybody know that, right? Is that percentage or value? So that's 0.9, right? And then you have this 4 point, actually, let's go with the watt, 4,312 watt, right? And then the time in 1 day, okay, watt means what? Joule per second, right? Uh, so 1 watt means joule per second, right? So the 1 day equal to how many hours? 24 hours. In 1 hour is 60 minutes, and one minute is 60 seconds. So that many seconds in 1 day, right? Okay, that means seconds per day. All right, and then you have this point 02. Okay, that's the cost, right? That's dollar per unit megajoule, right? Now you have this joule here and megajoule here. Obviously, there's a mismatch, right? So you gotta do what? Yeah. So you gotta divide by million to make it right. So 1 megajoule equal to 1 million joule, right? So then take a look here. What will happen? This megajoule gonna cancel out, right? This joule and joule gonna cancel out. This second and this second will gonna cancel out, right? So we're gonna have money per unit day, unit wise, and the value will be finding to heat up that basement floor. You're gonna spend, if you're gonna use the natural gas, around $9, right? No, $8, $8 and 29 cents every day, and that's a problem. So I know we're done, but let me give you an overview of what happened on the problem itself, right? So we're dealing with the conduction problem, right? So we use the conduction equation to find the heat rate. In the conduction equation, you have minus Ka del P over thickness in this case. The thickness given, is the surface area given, L multiplied W is given 1.4 1 per meter Kelvin, right? The negative goes away. Top and bottom surface are given for the basement wall. There is a negative came, negative become positive. So we have a heat rate, which is 4,000 something watt. So then we find the cost, natural gas cost, right, per day required. So we use this heat rate, okay, and we use the efficiency of that furnace that we are using to heat it up, right? And we use the efficiency, heat rate, and the cost per unit megajoule of the natural gas, right? And then we did some unit conversion to find the daily cost to heat up the basement floor, which is $8 and something cents. It's the problem. Okay, so again, there are homeworks in that space. Don't worry about all those. Just focus on homework number one. In that space, there is a Dropbox. As I said, please don't ever try to look for the solution manual. Nowadays, for ChatGPT, no matter how different problem I give, people start to find it that if you do that, then you are not doing any favor to yourself. You are actually destroying yourself. Okay, it's up to you which route you want to go. So do the problem by yourself. I suggest work in a group. That could be helpful, right? If you don't have a group and if you are shy, don't want to work with a group, just talk with me. I'll help you with my best. Okay? I have office hour on Wednesday, 1 to 2, right? My office. My office is 1118. Okay, 1118 is a lab. Okay, so there is a lab in front of my office next to Dr. Craig. My name is Dr. Roman. Okay, so just go over there anytime. If you have any issues with homework, I'll help you. And also, if you're interested, just work as a group. Don't try to look for the solution manual. Okay, these are possible problems. Try to do it. All right, guys. I'll see you again on Thursday. Okay, don't miss class as well.